Hi there. At the end of last video, we talked a little bit about how to filter compounds. I had later realized that I didn't set up enough calculations for compounds, leaving us with a limited supply of compounds to screen. So I actually want to go back and look at how to set up these calculations for screening all 3 million compounds all at once. So if I go into my docking folder where we stored all of these files, this is all of the docking. These are all of the tranches that contain all of the ligands that we want to dock. As we said, if we go into one of these tranches, these are the files that we would pull into Maestro. Being that each one of these files aren't very big, there's sort of a shortcut to getting to all of these files at once. If you just simply go back to the docking folder that we have here, and we go to the search bar and search GZ, or GZ if you're American. These are all the files that will actually pull into Maestro to dock. Me personally, with my computer setup, I've realized that I can screen in one Maestro workspace about 500,000 ligands before my computer has issues. So what I do is I can do 500,000 ligands personally, and with my license, I can do 5 different files. That would mean that I can screen 2.5 million compounds at a time, which is basically all of the compounds. So here's what I'm going to do. I'm going to open up a Maestro workspace. Okay. And then similarly, what I'm going to do here is, if there are 109 tranches, let's get a calculator. If we have 109 tranches, how many would I have to put in each file to do this all in 5? Divide by 5, we get 21.8 approximately. That's a decent way of doing it. So if we select 15, 16, 17, 18, 19, 20, 21. Let's see how many 21 gives us. Click, and that'll drag all my files into the workspace. While that's loading, okay, this is loading all the files in of the 21 file types, I can actually open up another Maestro workspace and do the same thing, because it will take quite a bit of time for all these molecules to load into the workspace. Go back, GZ, and if we go down to our do the same thing. Okay. 23, 20. Let's do 22 this one. Do the same thing, drag this into the workspace. And then what you would do is just keep going through this list until you've loaded all of the files into different Maestro workspaces. I know that I can run up to 5 QikProp jobs due to the license that I have with Maestro. Okay, so here we are back, and all of the files have imported. What we now simply want to do is, once the import is complete, as it says here, we'll press OK. It's always important to make sure that all of the files that you imported are selected inside of the table. I know they are because when you upload multiple tranches at a time in one go into the workspace, they'll all automatically be highlighted. If you drag and drop like one file at a time, they won't be automatically highlighted in the workspace. Okay, entries, about 5, almost 600,000. That's fine. 580,000 will work. And notice how they're all also selected. This isn't This is very like boring stuff, but it is practical knowledge when running these kinds of jobs. So I'll simply go to the tasks, go to QikProp, make sure use structures from project table. Yeah, project table selected entries. Job name, I'll name this the project CB1 QikProp. And this is the first file that I'm running, so I'll just do this as so. Go to just fix for all. This job will take about 2.5 hours to run, so of course I'm not going to stream for 2.5 hours. The second one, I'll just kind of maybe walk you through like one or two. Same thing, QikProp, project table. We're calling this CB1 QikProp 2 run fix. Go to the third one. CB1 QikProp. This is the third one we're running. Fix for all. And then my fourth one is here. Oh, whoops. QikProp. CB1 QikProp 4. With that being said, we'll touch base when all 5 of these jobs are done running. For my computer, this takes about 2 hours or so.
Okay, let's open up a Schrodinger CB2 project. Okay, now what we need to do is those files that those QikProp jobs have finished, we need to locate them. For me, they're in File Explorer, this PC, C drive, users, Asher, documents, Schrodinger, and for date modified, boom. And here are the QikProp jobs: 1, 2, 3, 4, 5. What we'll need to do is open each one of them and drag them into our Maestro workspace so we can filter the compounds. I'll show you how to do one, not necessarily all of them, because this filtering process does take a while, even with a pretty powerful computer. So to open one of these, the file you're looking for inside of here is the output file, which is right here. So I'm just going to make this a little smaller so I can see it as I drag it in. I'm going to click and drag it in, the output file. This one's not super big. I usually run about, like as I said, 500,000 per batch, but you know that sometimes can be smaller, it can be bigger. This one looks like it'll be about 100,000. Okay, we're done. That file has loaded. We can drag that out. Some of these compounds are quite funny. These are mainly because a lot of these that we downloaded early on, if you remember, were fragments. They weren't necessarily molecules, some of the earlier ones. We'll click table to display our table, and that's where we'll kind of filter all of our compounds from. We've got our file open, our QikProp job. What we have to now do is we want to delete out compounds that we do not want, that have properties which will not get into the central nervous system. Although CB2 is primarily located on immune cells inside of the body over the brain, I kind of want to look for a CNS active drug, one that gets into the brain. So we'll click one of the entries, okay, and that'll select one of the entries in this QikProp job. The filtering process I always start with is number of stars. Number of stars is basically a Schrodinger metric that tells us whether or not the compound will act drug-like or simply just like a molecule. And the more stars, the worse. So the way I filter this is click on the entry, click on stars, click on descending, and basically anything that is not a 0, we will delete out. It filtered for us. So now if we go back to stars, 15, some of these compounds are very bad, and that's totally okay. It's funny, I've never screened for molecules that are like small fragment-like, and I think that's why some of the star values are coming up so high, like 15. I've actually never seen a value of that. That's crazy. What we do is scroll down until we get to 0. Kind of find where it hits 0, 1. Somewhere around here. Okay. And as you can see, we quickly screen molecules out very quickly with this method. This is 96,000 molecules that will be deleted and gone. So we hold shift and then hold shift and click, and that'll select all 96,000 entries. I mean, right there, we're going to delete 96,000 out of 165. That's more than 50% of the compounds instantly just gone. That's why I like to, if you were to not pre-filter all these compounds and just dock them, that would use a lot of CPU resources that would, you use a lot of CPU resources that wouldn't be necessary because eventually you'd put this drug into a human or an animal for a trial and realize it has toxicity issues, it's not druggable, it doesn't really work. There's always a few compounds at the bottom that don't give readings because they are not in any way, shape, or form drugs, and no reading means we delete them out. You'll always end up with something that has like some problem atom typing or just doesn't even act anywhere remotely to a drug, and we delete those out. So, I mean, yeah, as you can see, the filtering process just deletes a lot of molecules, which is actually good. We don't want to end up with, like, having to dock millions of compounds. The next one we go over to is CNS. This will tell us the likelihood the compound will get into the brain. Negative value means it likely won't get into the brain, and a positive value means it has potential to actually cross the blood-brain barrier. Let's go to ascending. So CNS for Schrodinger metric starts at -2, meaning CNS inactive, and goes all the way as +2, which means it's definitely it's likely to be, I don't want to say definitely, likely to be CNS active. Okay. Come on, when's this gonna break? I usually, publications that have validated results using Schrodinger says that you can actually use values 0 to +2 or okay. Basically, there was a paper that looked at all of the current FDA-approved medications that cross the CNS and what were the output values from Schrodinger. And some of them actually had 0 for CNS activity, which is fine. And it's only really because computational methods are not, they're decent representations of reality, but they do have problems. You know, they're not completely accurate. They're not 100% accurate. They're pretty good. They don't work super well. That's why we have to actually run studies in animals and in people to make sure our compounds actually work. So CNS, okay, good, we've got that. The next one I go to is hERG. Go to ascending. Basically hERG, there's it's an ion channel called hurt potassium. I believe it's an ion channel. And compounds that bind well to hurt tend to be aromatic, and these compounds tend to cause toxicity issues. Basically, you inhibit this enzyme, this protein called hERG, and that causes issues. So basically, -5 is kind of the cutoff here. Anything that is -5 or more negative, we want to delete out for. Anything that is -5 or greater going towards 0, we keep. Well, I say we as in, this is just something I keep. Everyone has different screening methods when they screen compounds. This is just, these are metrics that I like to use. That's only 1,600 compounds down. We delete all those. We go back up. We've got 42,000 left. The next one is oral absorption. We want compounds that are highly absorbed orally. The cutoff I like to use is about 88%. I don't really have a good specific reason for it, just like doing this a lot. It's kind of what I've developed. You know, you develop your own SOPs as you kind of do experiments a lot, and this is kind of the one I found that works well. So we go to 88. The paper that I'm referencing also, maybe I'll leave that in the description, but it references you can actually use 62%. But I like to use 88. These are all personal preferences based on all the literature I've read, and they're by no means like correct. They're just preferences. Okay, and then we've selected 19,000. Delete. Cool. And we delete those 19,000 compounds. Sweet, this is looking pretty good. And you know, you quickly realize that we do delete out a lot of compounds. I did run the 155 control, which is the co-crystallized ligands, and as we can see, some of the characteristics of the Win compound, I think I talked about last time. Let's see, what are some of these properties for Win? Oral absorption, 100%, pretty good. hERG, -6.612, that is problematic. I actually would screen that out if I were doing one of my normal drug screenings. Other than that, it has pretty good care. CNS positive, CNS2 is really good. Star is 0. So yeah, I mean, other than hERG, this compound is pretty good. hERG would be problematic in a compound like this. What I would then do is I would drag in my other QikProp jobs that I've created. I'm not going to show you that because that would take like hours for me to actually do. I'll probably do that off video and show you the results. But what I would do now is basically once you compile all these compounds and screened out the ones that you don't want, you can select all the ones that you do want, which is 23,000. Also make sure you select the controls. We're actually using 155, 212, and it's an enantiomer. You could use more, you could use like THC. I always like to use the co-crystallized ligand. And then when I do the docking job, I select values that are higher than the co-crystallized ligand, which gives us a high probability the compound will actually dock to the receptor. This is, once again, a personal preference. Just, you know, I've been doing this for like 2 years. Isn't that long. Some of you that have been doing this longer, you may have different preferences for how you kind of screen compounds. Okay, so we've got all those selected, 23,000. Okay, whoops. I would then go to, actually, so I have to create a grid. Forgot one thing. We have to create what's called a grid file to tell our ligands where to dock. To do that, we go to tasks. We go to receptor grid generator. we pick the ligand that we're going to create the grid file for, which is the co-crystallized ligand in every receptor, which is this. It'll put this purple box around it. Okay, we can go to site. Oops. If you go to site, advanced settings, you can play with the size of the grid file. Notice how if I increase the number, the box gets bigger in the X, Y, and Z directions. Typically, if you know the binding site for the ligand, you can use 10 by 10 by 10, which is Maestro's default, and this is the one I typically like to use. We can name the file. This is our CB2 grid. And then we can put the date. Today's January. For me, January 30th. We can run this job. This job runs pretty quick. A grid, receptor grid generation should only take like 60 seconds to run. It's not a very highly intensive job. And it's done. We now need to go to ligand docking under glide. We need to select that grid file. Here it is right here. Double click, it puts it in there. Now we need to go to our table and select all the ligands that we want to dock to the receptor. Kind of show you how to do that. Whoops. Boom. Okay, we have 23,000 compounds. And then we have the control. And for fun, it's an enantiomer that we used QikProp to develop last time. It's fun sometimes to think about how why some enantiomers are not active at the same receptor, and it's basically because when a receptor recognizes a ligand, it doesn't care that it has carbons, hydrogens, nitrogens, oxygens. It just recognizes the three-dimensional shape of it, which is kind of globular, and also all the electrostatic charges. It doesn't care about atoms, right? It cares about the three-dimensional orientation of that thing. It doesn't give a crap about your carbons. Doesn't give a crap about what atoms are attached to it. So anyways, we've selected all those. At the bottom, it'll tell us we have 20,362 total, and we're selecting 23,328. We now go back to our ligand docking panel. And we already have our grid file. Settings. In the initial first screening, I always like to use high throughput screening. High throughput screening is the fastest method. As you go down to SP and XP, the computations become more precise, so they take longer. But in an initial screen, I like to use HTVS. It's pretty quick. This job will probably take my computer about an hour and a half or so. But if I were to run 23,000 ligands on like XP, that would take like 5 days. So whenever I initially kind of do a screen, I'm always starting at the fastest method to screen out compounds that definitely don't bind at all. Ligand sampling flexible. Rigid would be like rigid would mean that the ligands don't have any conformational flexibility. But flexible is what we want. It's good. It's going to be able to turn the single bonds and rotate them. That's kind of what we want. We can name this job. We'll name it CB2. This is like the first tranche, which is in what I named this is QikProp 4. And then I would also redo this for all the other tranches that I had, which were there were 4 other tranches for a total of 5 when I set this up before. And we can run this job. Oh, sorry, ligands. Oops. It's good. Use ligands from project table. Forgot to select that. And we'll run this. And I'll probably check in with you guys tomorrow after I've compiled all the files and run these. And we'll talk about, where we go from here. Ligand discovery using computers is actually, it's really cool in that you don't have to synthesize all these compounds and run all these through bioassays, which takes way longer than this. I consider being able to model this on a computer a privilege. It's a super cool, efficient way to be able to figure out what compounds are likely to bind versus not bind without having to do all the crazy legwork of synthesizing compounds and running them through functional assays, which takes a super long time. So I'll check with you guys tomorrow and hope you enjoyed this video and found it informative. Please leave any questions if you have any. Bye.